Hi, this is Matthew from BMI Academy. Today's class would be a revision on optics, basically the first part of optics, which is the conceptual part. So before I proceed, I would like to give a quick summary. So the question should be, what is optics? Optics is a science of light. Whenever you hear the word optics or see the word optics, think about light. So the science that governs light is optics. Okay. And what is light itself? Light is a type of wave that stimulates the sensation of vision. We can categorize light into two different forms of waves. It is an electromagnetic form of wave. And why so? Because it does not require a material medium for its propagation. All electromagnetic waves do not require material media for their propagation. So light is an example of such. And it is also a transverse type of wave because the direction of movement of light or the direction of propagation of light is always perpendicular to the direction of vibration of the particles. I mean the particles of the medium in which it moves in. So light moves in such a direction that is perpendicular to the direction of vibration of the particles of the medium. So in such situation, we can say that, light is a transverse wave. So what's now the complete definition of light? If you don't simply want to say light is a type of wave that stimulates the sensation of vision, just add um, um, additional information like light is an electromagnetic type of wave and a transverse type of wave that stimulates the sensation of vision. So another point you need to note is that light has a wave particle duality. It behaves as both wave and as a particle. Light also has a property called the rectilinear propagation of light, which is the ability of light to travel on a straight line in one direction. So what are the properties of light as a wave? These are the properties you should think of: reflection, refraction, diffraction, interference, and polarization. Reflection itself is the repropagation of a wave when it hits what? A boundary. For instance, if you have this to be a boundary between one layer and what? Another, or one medium and another. So if, for instance, we have light, this is an incidence of light, and here we have what they call what? Normal. So if the light eventually bounces back into the medium from which it was coming from, such is called reflection. So reflection is the repropagation of a wave. And for light to be repropagated or for light to be reflected, we need what? A smooth, shining surface. Refraction itself is the transmission of a wave from one medium to another. Or you can still describe it as the bending of a wave when it travels from one medium to what? Another medium that have different what? Optical densities. For instance, if you have something like this, and you have what? Light coming from medium 1 and eventually entering into what? Medium 2. Okay, so this kind of movement or this occurrence is called refraction. So most time the wave is going to bend away from its initial path of propagation. I'll talk more on that later. So we have diffraction itself. Diffraction is the bending of a wave when it meets an obstacle or an open slit along its path of propagation. For instance, if you have what? This to be a slit, and you have what? An approaching wave. So when the approaching wave, which we can call the incident wave, eventually gets here, what happens? In order to pass through these slits that we have here, it's going to bend. So the bending of this wave as a result of this obstacle placed along its path of propagation is called diffraction. So it doesn't have to be slits, it could be obstacle. So one of the major criteria for diffraction is that the wavelength of the wave has to be bigger than the size of the slit. If the wavelength is smaller than the size of the slit, diffraction is not going to happen. Then we have interference. Interference itself is described as the overlapping of what? Two waves. You get? When two waves overlap, in simple terms, we say that's what? An interference has occurred. We'll talk more on this later. I'll be more specific later. Then we have polarization. The polarization of a wave is a restriction in the vibration of a wave to a plane. If you can recall, that's what? Transverse waves. All electromagnetic waves are what? Are transverse in nature, which means the direction of vibration of the particles and the direction of the wave are always perpendicular. Okay, so for an electromagnetic wave, we have the electric part and the electric field and the magnetic field. So for instance, we have let's use the excuse me. So here we have a YX plane, and let's call this what? A Z what? Plane. Okay, so you can have what? A waveform along what? The XY plane. We can also have what? Another waveform along the what? XZ plane. Something like this. So here we have two different what? Waveform. Now, if we want to restrict the waveform that we have to a plane, instead of just having all the waveforms, in that case, we simply want to polarize the wave. So polarizing a wave simply means restricting the vibration of the wave, of the transverse wave, to a plane or to a certain direction. So instead of you having it vibrating in all directions, you just want it to vibrate in specific what direction or in a specific plane. Okay. So we'll talk more on that later. We'll be more specific. And we have properties of light as a particle. These are the following properties of light that guarantees it as what? A particle. We have the photoelectric effect, the Compton effects, black body radiation, laser what? Emission. What is photoelectric effect? It is the libration of electrons from the surface of a metal using electromagnetic photons. So when you use photons to generate electrons, we simply say that what you have created what they call photoelectric emission. So photoelectric effect is a particulate property. So Compton effect is described as the inelastic scattering of a wave as a result of what? Collision with a stationary charge or stationary electron. Okay, so for black body radiation, the black body is a body that absorbs um all the what, all wavelength falling on it. It absorbs all the radiations falling on it. Okay, so generally speaking, all heated bodies, they release what? Radiation of what? Certain wavelengths. Okay, this property is usually a particulate property. Then we have laser emission. So the word laser is an acronym to mean light amplification, light amplification, okay, for the stimulated emission of radiation. So light amplification of the stimulated emission of what? Radiation is what we call laser. So laser emission, because it involves what? Photons, stimulated emission in this case, it is a particulate what property. So in summary, these are the wave property of light, and these are the what? Particulate property of light. Now let's talk about reflection of light. Reflection, generally, like I've described earlier, is the repropagation of a wave. It is the bouncing back of a wave when it meets what? A boundary. Okay? So for we to examine the reflection of light, it is best studied with what? Plane mirrors and curved mirrors. So a plane mirror is just what? A glass that is coated at what? One end, usually with what? With silver. So that makes the other end, or the uncoated end, to be highly reflective. So here we have incidence radiation. We have the incident wave. Then here we've got the normal. The normal is perpendicular to the what? To the surface. And what do we have? We've got what? The reflected what? Ray. So things you need to consider here, number one, the angle of incidence, which is the angle between the line of normal and the what? Incident ray, is equal to the angle of what? Reflection, which is the angle between the normal and the what? Line of what? Reflection. So another thing you need to know is that what? The line of incidence, the line of normal, and the line of what? Reflection, they always meet at the same point, and they all exist on the same plane. So these are the laws of reflection. Number one, angle of incidence equals to what? Angle of what? Reflection. Number two, the line of incidence, the line of what? Normal, and the line of reflection are always meeting at the same point, and they all exist on the same plane. So please take note of that. Another thing you need to know is the glancing angle, which is the angle between the line of incidence and the what? And the plane or the mirror. So another thing you need to consider is the angle of deviation. The word deviation means shifting away from initial pathway. So if this is the initial pathway of incidence, and this now means the new pathway, which is the line of reflection, there is definitely an obvious what? Angle between the initial line of direction and the new what? Line of direction, right? So the angle between the former direction and the new direction is called the what? Angle of deviation. So take note of that. So So the angle of deviation is going to be twice the glance angle. Why is that so? This particular angle, which is the glance angle, is going to be equal to the angle here, because mathematically we call that vertically opposite angles. Since the angle of incidence, this is already equals to the angle of reflection, this, then we can tell that this angle here is also going to be G. Since this line is a line of normal, we expect the total angle to either side to be 90 degrees. So that implies that the angle of deviation is going to be what? Twice what? The glance angle. Okay. Then we have curved mirrors. I'm still going to talk more about the properties of plane mirrors. There are some questions at the end of this class which are more emphatic on information on plane mirrors. So I will take my time to explain when I get there. So here we have the concave mirrors and the convex mirror. So a concave mirror is just what? A curved surface. Generally, a curved mirror is a curved surface that is what? Coated at one end. So if we have this to be a curved surface and it is coated at the outer part of the what? Of the curve. So this makes what we call a concave mirror. So a concave mirror usually have what? A hollow side from your position of what? View. So if this is your position of view, what you are seeing is going to be the hollow part of the what? Of the curve. That makes it the concave what? Mirror. But if you have something like this, okay, let me redraw that. So if, for instance, we have this to be a mirror, I mean, a curved surface, and we have this part of this mirror to be coated. So automatically the coated side becomes the back of the mirror, while the uncoated side is going to be the front of the mirror. So which means as an observer, this is where your eyes will be. So because while looking at this, you'll be seeing a swollen surface or a bulge. We say that's what? That is what? A convex mirror. So a convex mirror always appear like a swollen surface. A concave mirror always appear like what? A hollow surface. So take note of that. So swollen is what? Convex. Hollow is what? Concave. This goes beyond mirror. It extends to what? It extends to lenses. It extends to lenses. Okay, for instance, hold on. Okay, hold on. I need to create some space. Okay. All right. So, hold on. I need to escape this. Yeah. So, like I said, swollen surface generally means concave. I mean, swollen surface generally means convex, while hollow surface generally means concave. So, for instance, now, if I have this, if I shade this part, that becomes the back. So whatever I'm saying here is hollow. That makes it concave, right? So if I have something like this and I shade this part, this makes it the back. Whatever I'm saying from this side becomes swollen. That makes it what? Convex, right? If this were to be lenses, for instance, we have what? This is a lens. Now, you realize that for a lens, you have two sides to observe from. If you observe from this side, it is swollen. If you as well observe from this side, it is swollen. So that makes it what? Biconvex lens. Why biconvex? Because the two sides are swollen. So this is what? A biconvex lens. biconvex lens, right? So similarly, if you have something like this, this is also another lens. Let me draw that properly. Okay. So if you observe from the left-hand side, you're going to see a hollow. Then also what? Observe from the right-hand side, you see a hollow view. So because both sides are hollow, meaning both sides are concave, so we can say this is what? A by what? Concave lens. Okay. So, and so on. I don't want to waste too much time on lenses because the focus is on what? Is on mirrors. So in an exam setting, what is mostly tested? They usually test the properties of images formed for an object that is placed at strategic position from the lens or from the mirror. Could be lens, it could be mirror. For now, our focus is on mirror. So the mirror I'm focusing on right now is what? A concave mirror. Why? Because this side is shaded, is the back. Then that makes what? This side to be what? The viewing part. So if this is what? The object, because I don't want this video to be too long, usually when you have what? An object positioned behind the center of curvature. Okay, I need to quickly explain some things. A mirror has what important parts you need to be familiar with. So if this is a curved mirror, the center of the curved mirror is called the pole. Like in this case, this center here, this geometric center of the what? Of the curved mirror is called the pole of the mirror. Then if the mirror were to be a complete sphere, if this is the mirror, if we were to make it a complete sphere, we expect it to have what? A center, right? So this is what I mean. If this mirror were to be a complete sphere, it's expected to have a center, right? So that center is called a center of curvature. Then if you draw any line from the center toward an external part of a sphere or a circle, it's usually called a radius. So the distance between the center of curvature and the what? And the pole is definitely a radius. So it is not restricted to center of curvature and pole. It also what extends to what? Any line you drawn from the center of curvature to the what? To the mirror is definitely the, what's it called? The radius of curvature. So it's better to know what they call optical what center, the optical center or the pole of the mirror. So you're also expected to know what they call the center of curvature. Center of curvature. You are also expected to know what they call the focal point. Focal point, or they call it the principal focus. Principal focus. So you're expected to know what they call focal length. Focal length. Which is usually denoted small letter f. And you're also expected to know what they call the radius of curvature. This is center of curvature here. So you're expected to know what they call the radius of curvature. So these are things they ask for in exam hall. I mean, for their various what definitions, right? So I'll quickly summarize that for you. So the optical center or the pole is called the geometric center of the mirror. So pole equals to what? Geometric center of the mirror. Pole again is equals to what? Geometric center of the mirror. Pole. Geometric center of the mirror. So it doesn't matter if it is a concave mirror or a convex mirror, the pole is still the geometric center of that mirror. Then we have the center of curvature. Center of curvature, let me denote it as CC. You know, I told you that a sphere is expected to have what? A center, right? So it is the imaginary center of the mirror if it were to be a complete sphere. Imaginary, you need to have that imaginary center of the mirror. So if the question say define center of curvature of a convex mirror or center of curvature of a concave mirror or center of curvature of a convex lens or concave lens, you need to be more specific when you are defining. For instance, if there is no specification in the lens or the mirror, I will just go ahead and say it is imaginary center of the mirror if it were to be a complete sphere. If it were to be a complete sphere, right? So we also have the principal focus. The principal focus is denoted what? Capital F. It is an imaginary point that exists between the what? The center of curvature and the what? And the pole. Or you can say it is what? An imaginary point on the principal axis. This particular line here, this line we have here is called the what? Principal axis. So the principal axis is an imaginary line that runs through the center of curvature and the pole of a lens or of a mirror. In this case, you are dealing with a mirror. So that point that lies on the principal focus such that all rays that are close and parallel to the principal focus pass through after convergence, after reflection, is definitely what we call the principal focus. I repeat, we have what? A line that is close and parallel to the principal axis. Usually, that line after reflection pass through a point called what? The principal focus, right? That's where the definition of principal focus comes from. It is a point on the principal axis where all rays close and parallel to the principal axis converge through or seems to diverge from after reflection. So you can take your time to write this down. I repeat, it is a point, that is the principal focus. It is a point on the principal axis such that all rays close and parallel to the principal axis converge to or seems to diverge from after reflection. If this question is about lenses, for instance, if the question says, define the principal focus of a lens, instead of using after reflection, in that case, you have to use after refraction. If the question is more specific, like define the principal focus of a concave mirror, because you know that a concave mirror converges, you need to be specific about the definition. This is how I would have defined it. The principal focus of a concave mirror is a point on the principal axis where all rays close and parallel to the principal axis converge to after reflection. You realize that I just lock it on what converge to, because the question is about concave mirror. If it is convex mirror, I'll use what? Seem to diverge from after reflection in that manner. Okay, so what are the properties of the images formed when an object is positioned at different location? There is a separate video for this. If you have seen it, that's fine. If you have not seen it, take your time to look for that on my page. Okay, so if an object is positioned behind a center of curvature, the image that is formed is usually around here. Now, I don't want to draw a diagrams for now. There is a separate video for that already. Okay, now if this is the object, what we have here is the what? Image. So what are the properties of the image here? Number one, it is inverted. You can say that the orientation of the image is what? Upside down compared to the object. Okay, there is a rule for drawing ray diagram. There is a separate video for this already. Just look for it on the channel. It's under optics. Okay, so it is inverted. Now compare the size. You realize that the size is smaller. So you can say it is what? Smaller, right? Okay, smaller. Or you can say reduced, or you can use the word diminished. Diminished. Okay, and what else? The positioning, it is formed between C, that's between the center of curvature and the principal focus. Formed between center of curvature and what? The principal focus. That's the positioning. Okay, now let's talk about the nature. I want to know if this is virtual or real. This image here is a real image. Real what? Image. Now, how do I know that this image is real? As an observer, this is the side you're going to stay. You are staying on this side. This is the side of the what? Observer. And whenever an image is formed on the side of the observer, the image is always real. Now, don't get me wrong. This is an object here. Object does not necessarily mean observer. The observer can be you. So let me say this is your eyes here. You are the observer. You are trying to observe what is happening to this object and to observe the image of the object. So if, for instance, this were you, this standing object here, if you were the one, it means you are being two things at the same time. You are the object and you are also the observer. Whichever the case is, whenever an image is formed on the side of the observer, the image is real. When the image is formed at the opposite side of an observer, the image is virtual. Don't get me wrong. I didn't say object. I'm using the word observer. Whenever an image is formed on the side of the observer, the image is always real. Whenever the image is formed on the opposite side of the observer, the image is always virtual. So just take that as what? As the fact. So the image here is what? Is real. Real image. So these are the properties of images formed when you position an object behind the center of curvature for a concave mirror. When the object is positioned on the center of curvature, the image is usually formed here. Like I said, there is a separate video for the ray diagrams. This video will be too long, drawing ray diagrams here. So the image, this is the object, this is the image. So the orientation, number one, it is what? Inverted. Number two, talking about the size, is same size as what? Object. Number 3, talking about the position, is formed at what? At the center of curvature, meaning it's formed back at the center of curvature. Then talking about the nature, it is real. Why is it real? Because it is formed on the side of the observer. When the object is positioned between center of curvature and principal focus, the image is usually what? Formed around here. Try draw the ray diagrams after watching the other video. Okay, so what do we have here? We have number 1, the image is inverted, that's the orientation. Number 2, the size, it becomes bigger, right? So we say it is magnified, or whatsoever grammar you want to use to represent that. Then let's talk about the position. It is formed behind the center of curvature, behind CC. And number 4, let's talk about the nature. It is real, since it's still formed on the side of the observer. So what happens when an object is placed on F, on the principal focus? In this case, the image is formed at infinity. Because when we draw ray diagrams here, let me try draw a ray diagram for you to see. I have an incidence from the head, then I get what? A reflection through the what? Principal focus. Then again, if I have what? A ray through the head, okay, so we have both incidence and reflection along the same what? Pathway. So what we end up having is 2 parallel lines as my reflection, 2 parallel lines. So because the lines are parallel, there is no way for them to meet. Since they cannot meet, we say image is formed at infinity. So since the image is formed at infinity, I can't tell other properties of the what? Images. We can only guess. Another case, when the object is positioned between the principal focus and the pole of the what? Of the concave mirror. Now, the image that is formed after drawing the ray diagram is always what? Around here. Okay. For you to understand this, let me just quickly draw the ray diagrams here. If you have this as the incidence, so we're going to have this, has to be straight. We're going to have this as the reflection, right? So if we have another line drawn from what? From the center of curvature to the mirror, glancing the head. So here we are going to have this to be what? The reflection. Now you realize that if you look to the left-hand side, the reflection here versus this reflection, there is no way they will meet because it's getting bigger, like it is diverging at this side. But because the lines are not parallel, if it is diverging on the left-hand side, it's definitely going to be converging on the right-hand side. So we have something like this. So the implication is that what? The ray will eventually what? Meet at this point, and telling us that what? The image will be formed here. So that tells us the information of the image that we need. Let's first talk about the orientation. If you compare the image to the what? Object, you would realize that what? The image is standing upright as so. So the image is upright, or you use the word erect. Number 2, let's talk about the size of the image. The image is bigger than the object, so we say it is magnified. Let's talk about the positioning. It is formed behind the mirror, So let's talk about its nature. The nature of this sort image. I want to tell if it is real or virtual. You just need to ask the question as an observer, where am I going to stand? Am I going to stand on the left-hand side or on the right-hand side of this mirror? This mirror is coated on the right-hand side. So meaning the right-hand side is the back. I cannot stand at the back because that will make me insane. So as an observer, I should be on the what? Left-hand side. So as an observer being on the left-hand side, the image is on the right. It's not on my side. That makes it virtual. So the image is what? Virtual. Okay. Then the last case here is that of a convex what? Mirror. For a convex mirror, the positioning does not matter. It doesn't matter where you stand. The properties of the image form is always what? VED, which means virtual, erect, and what? And diminished. Virtual, erect, diminished. So in exam setting, you can be told to draw the ray diagrams. So for instance now, if I want to draw the ray diagram here, let's say we have this to be the object. So I'm going to draw a ray parallel to the principal axis to the mirror, right? Then don't forget that I can't just draw a ray through this. It's not a lens. A mirror always what? Reflects rays. So if it is a lens will refract it, like it will just pass through. But in this case, it has to be reflected. So will I just reflect it anyhow? No. It has to, for any ray that is parallel to the principal axis, the reflection has to seem as if it is coming from the word principal focus. You get that? Then for any ray, I cannot draw another one either through the center of curvature or through what? Through F. So if I draw, let me draw the one through, I just need to make a fake cut. Okay, good. So let's say I have that broken line connecting the head to the center of curvature, and I have a ray traveling from the head to the center of curvature. So what we are going to have is we're going to have incidence and reflection happening along the same path. So the line of reflection for the first one, let's call it R1, and the line of reflection for the second one, let's call it R2, definitely meet at this point. So that means this is where the image is going to what? Form. So if you look at the image, in terms of orientation, it's standing the same way as the object. That makes it what? Erect. In terms of what's it called? In terms of the nature, as an observer, you are on this side. Because as an observer, you are on the left-hand side, while the image is on the right-hand side. That makes the image virtual. So it is what? Virtual. Then in terms of size, if you compare the image to the object is bigger than the image, or you say the image is smaller, so the image is diminished. So this summarizes the properties of images formed by mirrors. Now, this is very similar to the case of what? Of lenses. In fact, a concave mirror, a concave mirror, hold on, has similar properties to a convex lens. Please take note of that. Concave mirror versus convex lens. Similarly, a what? A convex mirror, it has similar image characteristic to what? A concave lens. So please take note of that. Concave mirror, this is it here. Convex lens, this is it here. Okay. Convex mirror, this is it here. And what? A concave lens, this is it here. So a concave mirror is a convergent mirror. This is convergent. A convex lens is also convergent. So convergent mirror has the same characteristics as convergent lens. A convex mirror is a divergent mirror. It diverges images after reflection. A concave mirror is also diverging. This one diverging, it diverges what? Rays after refraction. For lenses, the divergence or convergence happen after what? Refraction. For mirror, the what? Convergence or divergence happens after reflection. Please take note of those key distinctions. So let's move on. So we have refraction of light. For refraction of light, refraction generally is the um, bending of a wave when it moves from one medium to what? Another medium, such that the two media have different optical densities. Or you can say it is the propagation of a wave from one medium to another medium. I repeat, it is the propagation of a wave from one medium to what? To another medium. That is what refraction is. Then we have the loss of what? Refraction. Okay. I will use the next page to explain. But for refraction to be well studied, we make use of rectangular prisms, triangular prisms, and we make use of curved surfaces. And the curved surfaces are concave lenses and convex lenses. Okay. So this, let's call it a glass. Let this be a rectangular prism. So let's call this medium, let's call it air, and let's call the other medium here, let's call it glass. Okay, there is something I needed to know for what's it called? For air, materials you need to get used to are vacuum. Vacuum means there is no material medium itself. Then you get familiar with air, get familiar with glass, and you get familiar with water. When it comes to refraction, just get familiar with what? These four media and this, which is what? Vacuum, get familiar with them. For instance, for vacuum, the absolute refractive index is 1. For air, absolute refractive index is approximately 1. For glass, for Paris glass, absolute refractive index is approximately 1.5. If it is not going to be 1.5, you use what the question gives you. Or if the problem has to do with you determining it, you use the information supplied. The absolute refractive index for water is approximately 1.33, or which can be approximated to what? 4/3. So please get familiar with this information. And in one way or the other, there is, for most cases, there is a a direct relationship. No, don't let me use the word direct relationship. There is almost a direct relationship between absolute refractive index and optical densities. So from what you can see, absolute refractive index is greatest for glass, followed by water, you get? And absolute refractive index generally means the speed of light in vacuum over the speed of light in a given medium. So please take note of that. Speed of light in vacuum over speed of light in a medium. And since speed of light is greatest in vacuum, we expect the value of n to be greater than 1 for most cases. And the worst case scenario it could be, it should be 1. It should never be less than 1. So absolute refractive index cannot be less than 1. So in other words now, glass has the highest optical density among these four things I listed here, followed by water, followed by air, and the smallest value is the reference, which is vacuum. Please take note of that. So when it comes to refraction, a ray can either travel from a less dense medium to a denser medium, like in the case of air to glass. Don't forget that M has an optical density of 1, and glass has, sorry, N has what? What was it called? It has absolute refractive index of 1, and glass has absolute refractive index of approximately 1.5. Okay. So when a ray travels from a less dense medium to a denser medium, the line of refraction always come closer to the normal. You realize that the initial pathway was something like this, right? You realize that this is the new pathway, like this movement. So when a ray travels from a less dense medium to a denser medium, the line of refraction comes closer to the normal. It reverses the case when it moves from a denser medium, like glass, to a less dense medium, like what? Like less dense medium, like it could be water, it could be air. Let's use air. So in this case, when the ray travels in this manner, the line of refraction always go what? Away from the normal. Please take note of that. You realize that this was the initial pathway of incidence, and you realize that the refraction has moved away from what? The normal. Summary: when a ray travels from a less dense medium to a denser medium, the line of refraction comes close to the normal. When it travels from a denser medium to a less dense medium, the line of refraction is going to what? Go further from the what? Normal. The word normal means at an angle 90 degrees. This line here, that is making angle 90 degrees to the boundary. So what are the things you need to know here? You need to know what they call Snell's law. Before Snell's law, this line you see here is the line of incidence, right? So that's the line of incidence. Let's put the arrow. And this line you have at the other hand there is called the line of refraction. Okay. So this is medium 1. Why this is medium 2? I will just generalize them as medium 1 and medium 2. So we have angle, an angle here, and another angle here. So I'm going to label the angle theta 1 and what? Theta 2. Okay. So rather than just call them angle of incidence and refraction, I will just call them theta 1. And here I'll call it what? Theta 2. Okay. The number one thing you need to know is that the line of incidence, all right, and the line of what? Refraction. They both exist at the opposite side of the what? Normal. See, this is the normal. So both of them exist at opposite side of the normal, What else again? They also all meet at the same point, and they all as well exist on the same plane. So we can take that as a first law of what? Refraction. That's what? The line of incidence and the line of refraction exist at the opposite side of the normal, and they all meet at the same point, and they lie on the same plane. I repeat, the line of incidence, line of the what? The refraction, they exist at the opposite side of the what? Normal. And they all meet at the same point, which is here, and they all exist on the same plane. Please take note of that. Those are the key words. Exist at the opposite side of the normal, meeting at the same point, and lying on the same plane. So the second statement, which we can call the second law of refraction, is what we call Snell's law of refraction. So what that states is that what? The ratio of the sine of angle of incidence to the sine of angle of what? Refraction is always a constant for a given pair of what? Media. So it's telling us that when a ray travels from one medium to another, the ratio of the sine of angle of incidence to the sine of angle of refraction is always a constant for any given pair of what? Media. So generally that constant is usually denoted, in some cases they use the symbol eta. In some other cases they use the symbol mu, something like this, the symbol mu. So whichever case or whichever symbol they use, you're less concerned. This is called the relative refractive index. There is a difference between relative refractive index and the absolute refractive index. The absolute refractive index is the ratio of the speed of light in vacuum to the speed of light in a medium. Please take note of this. Okay. So why the absolute refractive index is from the word, sorry, why the relative refractive index from the word relative you are comparing. This medium has N1, this medium has what? N what? 2. Okay. And this line is traveling from 1 to 2. The refraction happens in 2. Don't forget that refraction is the movement of a wave, is the propagation of a wave from one medium to another. The line of refraction happens within what? Within 2. So if a question asks you to get the relative refractive index in this situation, let me clean this for space. So because this ray is traveling from 1 to 2, what we are going to have is that what we have something like this. This indicates traveling from 1 to 2. And this is going to be N2 over what? N1. Similarly, if the ray was traveling from 2 to 1, if I reverse the arrow, so this is going to give us what? N1 over what? N2. So please take note of that. When a ray is traveling from 1 to 2, the relative refractive index is N2 over N1. And when a ray is traveling from 2 to 1, the relative refractive index is going to be what? N1 over N2. All right. Another thing I need you to know is an alternative way to write Snell's law. In fact, that's the best way to what? To memorize Snell's law. You can do N1 sine theta 1 equals to what? N2 sine theta 2. Okay. So, and for the sake of quick solution, we have N1 lambda 1 equals to N2 lambda 2, where lambda represents the wavelength of the wave. Lambda 1 means the wavelength of the wave in medium 1, and lambda 2 means the wavelength of the wave in medium 2. And N1 and N2 simply means the absolute refractive indices of the media. Then another thing you need to know is the speed. N1C1 equals to what? N2C2. C1 and C2 means the speed of light in those media. So the media might be any two medium the question is talking about. Any two media the question is talking about. So just know what you're doing. All right, moving on. This is a triangular prism. Triangular prism. Okay, things you need to know about triangular prism. Normally the 3D diagram would have looked like this, something like this. So this is a prism that has a triangle as its what? As its cross section. So this is how a triangular prism looks like. So I'm more interested in the cross-sectional part, which is the triangular part. So I'm going to clean this 3D diagram and focus on the 2D. So here we have the incidence. So I'm going to place an arrow there to indicate incidence. So when it gets here, we draw a normal. This line here is the normal. So this angle here becomes the angle of incidence. Then what's going to happen here? Refraction will happen. And that makes this angle here angle of what? Refraction. This ray that was refracted from boundary, let me label this as A, B, C. Now we have boundary AB here and another boundary what? BC here. Okay. A reflection from boundary AB, which is this, automatically becomes an incidence to boundary what? BC. So we have this to be the normal. Then we eventually have a new reflection if this were to be the incidence. Now this reflection here is usually referred to as the emergence. So this is what? Emergence. And this is referred to as the incidence. Yeah. So what are the things I need you to know? I need you to know that, okay, let me use a better diagram. Okay. So if I extend this line further, this was the initial pathway of the incidence. Since the line has shifted this way, you know, this is incidence, refraction, right? Sorry, reflection. Sorry, refraction. This is refraction. That makes this angle here a small deviation. Similarly, when this one gets here, after drawing the normal, we draw an emergence, which is this. So we still have another what? Angle here, which is another deviation. So what do we have? If we extend this line this way and compare it to where the ray was originally coming from, don't forget that the angle between an initial pathway and a new pathway is an angle of deviation. So this particular angle you have here, this angle here, is called the what? Deviation of the what? The major deviation of the ray. So what are the formulae you need here? Number one, let's call this medium 1, medium 2, and medium 3. So you need to know that what? N1 sine theta 1 equals to N2. Let me shift this to the side. Let me change the ink for a good contrast. So I have n1 sine theta 1 must be equals to n2 sine theta 2 must be equals to n3 sine theta 3. Please take note of that. Of course, you can use the two equations simultaneously. You just have to probably pair them depending on the information you have, like this and this. It could be 1 and 3, your choice. So also know that if what you're dealing with are wavelength, still feel free to do this. N2 lambda 2 equals to N3 lambda 3. And if what you need are speeds, also feel free to say N1 C1 equals to N2 C2 equals to N3 C3. These are easy formula to make use of. Okay. Then some cases, the question, this, I forgot to talk about this angle here. This particular angle, let's go back here. This particular angle here is called the optical angle of the prism. Optical angle of the prism is usually denoted A. If this triangle here is equilateral triangle, you know what equilateral triangle is? All the angles are the same and all the sides are the same. So that automatically means that what? A equals to 60 degrees for an equilateral triangle. Equilateral triangle. Please take note of that. A is called the optical angle. Optical angle of the prism. Optical angle of the prism. That's what A stands for. Please take note of that. So I stand for angle of incidence. E stands for emergence angle. In some texts, you're going to see this as I1 and I2. All those things do not matter. Just know what you're doing. Okay. Mathematically, this angle here, A, is also equals to this angle here, A. Unfortunately, I can't start explaining that now because it's going to make this video unnecessarily what? Longer. So, what are the things you need to see here? Number one, you need to know that what? I plus what? E is always equals to what? A plus D. So there won't be time to prove this formula. It's a straightforward proof though. But take note of that. I plus E equals to A plus D. You need this formula should in case the question supplies you three of this information and is asking you to find one of them. Okay? Please take note of that. And based on this diagram, this angle here equals to sum of opposite what? Interior angle. Don't forget that in a triangle, the exterior angle is equals to sum of opposite what? Interior angles. A equals to what? R1 plus R2. And again, D, this D here is also equals to D1 plus D2. Same reason. Exterior angle equals to sum of opposite what? Interior angles. Take note of that. And another thing you need to know is that this angle I here equals to everything here, vertically opposite angles. So which means I is equals to what? R1 plus D1. And again, E equals to what? R2 plus what? D2. In fact, from here, you can easily tell why this particular equation came to life. You can easily tell if you had I plus E together here, if you had these two together on the left-hand side and adding these together, you realize that this alone add together as R1 plus R2, this is the A you have here. Similarly, this D1 plus D2 is going to be equals to the capital D you have there. So these are the formulae you need here. And should in case there is something called minimum deviation. Okay. Please also note sometimes they can give you information on minimum deviation. The absolute refractive index being sine I over sine what? R. So at minimum deviation, I need space. Just hold on. Okay, let me take this off here to create more space. So at what? Minimum deviation. So the things you need to take note of is that number one, the minimum means minimum deviation. So number one, you should know that I, which is the incidence, is equals to E at minimum deviation. I equals to E. This I is not equals to E at all times. I equals to E at minimum deviation. Okay, R1 is going to be equals to R2. Let's call it R. That automatically means that what? A equals to what? To R. Since A equals to what? R1 plus R2. So in that case, R becomes A over what? 2. Right? So take note of that. And do not also forget that since I plus E equals to A plus D, and I is already equals to E, so I can say I plus I, which is 2I, is not going to be equals to A plus, this is now D minimum. You know, the condition is minimum deviation. So that means I equals to what? A plus what? D minimum over what? Over 2. So that means that this that you have as sine I over sine, you know, I gave you that what? We have sine I over sine, over sine R. So our eta, which is the relative refractive index of the prism, can now be equals to sine I. Was our I? A plus D minimum over 2, then divided by sine R. And what was our R? A over 2. So take note of that. If the question gives you information of minimum deviation, feel free to use this formula. Moving on. Okay. Because of time, I just had to limit those explanations to that. We have way more to talk about, but while solving problems, we'll talk about some of them. Not all. I can guarantee you that. We have critical angle and total internal reflection. If you can recall, we discussed rays traveling from a denser medium to a less dense medium and vice versa. When a ray travels from a less dense medium, like from air to glass, the line of incidence come closer to the normal. But when the ray travels from a denser medium, like from glass, to a less dense medium, like air or water, the line of refraction travels what? Away from the normal. So you realize that in the first case I have here, angle I is obviously bigger than R, right? And in the second case, where the ray travels from a denser to a less dense, angle I is less than what? R. So which means if you continue to increase high, of course, R also will continue to increase. But you can easily tell the one that's going to get to angle 90 first. Obviously, it's going to be R in this case. R will get to 90 before what? Before I. Okay, so that takes us to what they call the critical angle. Here I have a ray traveling from a dense medium to a less dense medium. Please, that's the first condition that must be met for both critical angle and total internal reflection. Without mentioning that, you are not defining critical angle nor total internal reflection. So the first thing is that a ray must travel from a denser medium to a less dense medium. So you can see this is what we have. Now, this is the incidence versus the what? The reflection, which is the refraction, I mean. So when you further increase the angle of incidence, we have something like this. So it gets to a point whereby the angle of reflection, sorry, the angle, why do I keep making this error? The angle of refraction gets to 90 degrees before the angle of incidence itself. So this occurrence is what they call, this angle here, this special angle of incidence here, at which the angle of refraction equals 90 is what they call the critical angle. The critical angle is defined as the angle of incidence at which the angle of refraction equals to 90 degrees for a ray traveling from a denser medium to a less dense medium. So critical angle is the angle of incidence, at which the angle of reflection, sorry, no reflection, at which the angle of refraction equals 90 degrees. Stopping here, you are not going to get your full mark because you've not included the condition I talked about, which means a ray traveling from a denser medium to a less dense medium. So you had for a ray traveling from where? From a denser medium to a less dense medium. Please forgive the space management. Okay, so that is what you call critical angle. Okay, then what is total internal reflection? Total internal reflection. Okay, still on critical angle. At critical angle, the angle of reflection was 90 degrees. What happens when we further increase this incident angle beyond the critical angle? So this is what you mean. If we have an angle here that is greater than C, in the second case here, we have I equals to C. But in the third case here, I is greater than C. Don't forget that the refraction was already at 90. So it has no other choice other than to enter what? The prism in this case. So it was initially at a region here before. Now it's going straight into the what? Prism. So the fact that it has gone straight into the prism means it has transformed from a refraction back to a reflection. You get that? So total internal reflection is just a phenomenon that happens when the angle of incidence is greater than the critical angle for a ray traveling from a denser medium to a less dense medium. So I will say total internal reflection is a phenomenon. It's a phenomenon which occurs when the critical angle of a medium is exceeded. You don't just stop there. You still need to put that indicator is exceeded for a ray traveling from a denser medium, to a less dense, medium. So you get the gist. So for total internal reflection to happen, a ray must traveling from a denser medium to a less dense medium, and the critical angle must be exceeded. Critical angle itself is defined as what? The angle of incidence of a ray traveling from a denser medium to a less dense medium, at which the angle of refraction is equal to 90 degrees. You get that? Total internal reflection can only happen when the critical angle is exceeded and when the ray is traveling from a denser medium to a less dense medium. One of its applications is in optical fiber. Application of total internal reflection. Okay, so it is applied in optical fiber. Okay, and let's say radio transmission. We make use of total internal reflection. So we also make use of it in explaining optical illusion. Okay, etc. I would say I would really like to explain a bit of that because it is needed. Okay, so what is an optical fiber itself? An optical fiber is just a device that is used for transferring signals. It's used for transmitting signals from one point to another without much leakages in the signal. So it's made up of a flexible glass or flexible plastic. Let's say this is the flexible plastic. Okay, so the flexible plastic is designed in such a way that we have it coated with something else. Okay, let's say you have something like this. I just need you to be patient. Okay, so let's say we have okay, let's say we have this. Yeah. So this is just showing a section of it. This is a sectional view. I mean, a section, you section a part out of the optical fiber. So it is designed in such a way that a ray that is traveling that enters from one part is internally reflected back. So you have something like this. So you can see what we have. The ray is being internally reflected till it moves from the source to the destination. So what is happening here? We have two different thicknesses here. Let me indicate it. So we have this thickness here. This has to be a material. This has to be a material with high optical density. This is a denser material. Is denser. Okay. So why the other material is less dense? Don't forget that it is expected for a ray to travel from a denser medium to a less dense medium. So this part here is denser, while this other part here is what? Is less what? Is less dense. Okay? Less dense. So the ray is trying to travel from a denser medium, which is the pink, to the less dense medium. And the angle of incidence is happening at a value that is greater than the critical angle. Don't forget that I said the critical angle has to be exceeded. So if that is happening, rather than we having a refraction, normally we should have had a refraction, but instead what we have an internal what? Reflection. Do you get that? So this is how optical fiber works. It's made up of materials, flexible glass or flexible plastic that is coated by a material of what? Of lower optical density.